All right, so today we're going to continue on with our 7.1 discussion with exponential growth and exponential decay. But now we're going to see a couple of places where it is used, okay? Exponential growth and exponential decay are used in lots of different aspects of everyday life, depending on what your everyday life entails, actually. They use it a lot in chemistry. They use it a lot in biology. They use it a lot in finance. Okay, banks and credit cards and all that kind of stuff use exponential growth and exponential decay. So let's go through and see these two aspects. So first off, if we're talking about exponential growth, like we did yesterday,
Ian Mooney, please come
we know that it
discussion.
follows this pattern for the equation. Y equals A times B to the x power, where B had to be bigger than 1 for it to be exponential growth, right? Well, therefore, the B is called the growth factor. That's telling us how much it's growing by each time. Okay, we're multiplying it by that factor of B every time. Okay, so a quantity that exhibits exponential growth can increase by a constant percentage. If we say that's going to grow by 30% each time, we change our B value a little bit. Okay, think back to the financial problems we did, the shopping problems we did, right? If I said that there was a 30% decrease, we took the price of our item minus the 30%, right? We had to take 30% of that item. And so we said that if we have $100, because it was easy to work with, $100 minus 30% was basically 100 minus 30. It gave us a cost of $70. Well, same thing here. 1 is 100%. So any item is 100% of itself. If I'm going to add 30%, then I'm going to add on 0.3 to 1. I'm adding on that 30%. So therefore, a growth factor or a rate of increase is going to be, our B is now going to be substituted with 1 plus R, where R is that percentage of increase. Okay, so if it's growing by 30% each time, then our B value is going to be 1 plus 0.3 or 1.3. That's going to be our growth factor. Now, the decay factor, same concept, but now remember it's decaying exponentially. That meant that our B value was between 0 and 1. So B is our decay factor. And so then again, we can have our percentage decrease. R is then our percentage of decay, or rate of decay. And now the book likes to go through and just call it still 1 plus R. Okay, I personally don't like to do it that way because it gets confusing to me. Okay, I prefer to keep my percentages always positive and think to myself, am I adding it on? Is it increasing? Or am I subtracting it away because it's decreasing? Catch what I'm saying? So I don't use 1 plus R when I do these. Okay? My B value for a decay is 1 minus R. So that I know that if I'm decreasing by 30%, I know that I'm taking 1 minus 0.3. I'm subtracting the 30%. You with me on that? Yeah. So we have percent increase and percent decrease for our exponential growth and decay. So the way we're going to rewrite our formula, because please remember that this comes from y equals a times b to the x. Rather than saying y, we're going to use function notation, and we're going to call it a of t, a standing for the amount. A of t, t standing for the number of time periods, usually years, okay? But number of time periods is t. So a of t is our y value, and t is our x value, our input. Little a, still from the same formula, little a now stands for the initial amount, which it always did, because little a was the y-intercept, correct? So if we start at time being 0, because remember, we're not time travelers, we can't go to negative time. So if we start at time 0, the y-intercept is our starting point. So that kind of makes sense why that is. So our initial amount is A, and then our B value is now replaced by either 1 plus R if it's exponential growth, or 1 minus R if it's exponential decay. Okay? And again, that goes along with what we were saying yesterday. Exponential growth is when the b value is greater than 1. So of course, 1 plus r is going to be greater than 1. And we said that exponential decay was when b was less than 1. So therefore, again, it makes sense that 1 minus r would be for decay. Any questions on just the equation so far? So we are going to use this equation now. A of t equals a times 1 plus r, or 1 minus r, raised to the t power, when we have a growth or a decay that is exponential, okay, and increasing or decreasing at a fixed percentage rate. Okay, increasing or decreasing at a fixed rate. So let's try an example here. We are going to model exponential growth. And our example here is that we are investing $1,000 into a savings account. So it says we invested $1,000 in a savings account at the end of the 6th grade year. So apparently you have a rich grandparent that gave you $1,000 for your birthday when you were in the 6th grade. Okay? So if that was the case, and you then put it into an account that pays 5% annual interest, how much money will be in the account after 6 years? Okay, because you're earning interest on that account, of course, every year. Something like this is called simple interest. We'll talk about something called compound interest tomorrow, which is actually more realistic when talking about real life situations. Something else I want to talk to you guys about real quick, just trying to show you the real life versus this math example for class. An account that pays 5% interest really probably doesn't exist. Okay, I have a savings account for my family, and I think we get like 1% or 0.02%. I mean, we get something ridiculously small. Okay, if you ever find an account that pays 5% interest for you, borrow money from friends and family to throw into that account, because that is unheard of. Okay, they don't do that when they're paying you. Okay, now on the flip side, a percentage like that for interest is totally good or totally valid. You'll see this out in the world if it's interest that you have to pay, like interest on credit cards, or interest on a home mortgage, or interest on a car loan, or things like that. If you're paying the interest, 5% is absolutely something you might see. Okay? Credit cards, a lot of times like to have you pay 15 to 20% interest. Yeah, big deal. Okay? Student loans. Student loans are sometimes down around the 3 or 4% interest for a student loan. So if you're paying the interest, absolutely you're going to see something around 5, 6, 7, maybe 10 or 15. But if you're receiving the interest, if you're making the money, very few things out in the real world will pay interest that high. Okay? So just kind of giving you a little bit of foresight there. All right, so let's say that this is true. Let's say we have this. We then want to invest our $1,000 into the bank, into our savings account. So the first thing we're going to do is we got to decide, is this exponential growth or is this exponential decay? What do you think? Growth. How do we know? Well, first off, obviously it says in the problem, exponential growth. Okay? But the other reason would be is because think of how a savings account works. You put money in, and then it grows a little bit, right? When you finally withdraw that, we're withdrawing more money than what we put in. That's what interest is. They're paying us interest. So that is a growth concept, not a decay. Decay, of course, would be you put in $1,000 and 6 years later you take out less than $1,000. It cost you money to put it aside. So we're going to use exponential growth. So therefore our equation is going to be a of t equals little a times 1 plus r, because it's growth, raised to the t power. Something to keep in mind here. I've told you guys this at the beginning of the year, multiple times throughout the year. I'm sure your geometry teacher told you the same thing. In math, if they give you a variable, that's the variable you have to use. Meaning, they give me a capital A and they give me a lowercase a. Those two A's stand for different things. That's why one's capital and one's lowercase. You can't interchange them. Okay? A lot of times I see this with B's. For some reason, students don't like writing lowercase b's. Everybody changes it to a capital B. You can't do that. Little b means something. Capital B means something. Okay? Use the variables that they give you and use them in the form that they give you. Don't start changing stuff around just because you like to write capital A's better than lowercase a's. Okay? They mean something. All right. So the capital A in this equation means the amount after our time period, right? So that's what we're solving for. How much are we going to withdraw in 6 years? So it's going to be capital A, and then the t is going to be 6, because we're talking about 6 years. So A of t is that function notation. The amount after 6 years. So little a, how much did we start with? $1,000. $1,000. And then we have 1 plus R. What is R? What's our percentage rate? Okay, 5%, which as a decimal is 0.05. And we are then raising that to the 6th power, because our time period is 6 years. Okay, so we need to simplify this down a little bit. So we have 1,000 times 1.05 to the 6th power. We need to take a calculator for this. Yes, you get to use a calculator on this. On the test, by the way, I fully expect you guys to be able to graph y equals 2 to the x power or something like that without a calculator. That is a reasonable explanation, or reasonable expectation, excuse me. Because on the test, there will be 2 parts to our test on this, right? One part will be no calculator, one part will be with a calculator, just like our Unit 5 test was. I would expect you to be able to do this problem, y equals 2 to the x power, and graph it without a calculator. Now, a problem like we're solving right now, no, absolutely you would get to use a calculator on this. So make sure you dig out those calculators and have one available. All right, something else that you're going to want to know. Something else you're going to want to know. On your calculator, to do exponents, you do not need to take 1.05 times 1.05 times 1.05 times 6 times. Your calculator will do that for you. Okay? But you need to know how to do that on your calculator. So everybody take a look at your calculator. If you don't have a calculator out yet, then get it out. But your calculator should have one of 2 buttons. Your calculator should have a button that says y to the x power, or your calculator should have a button that is just a little caret. Okay? It's called a caret. It looks like a little arrow pointing up. Okay, so please raise your hand if you have a button that says y to the x power on your calculator. A couple of people, okay? Everybody else must have the caret then? Yes? Okay. So these buttons, the way they work is if I want to do, let's say I'm just doing the problem here. I want to take 1.05 and raise it to the 6th power. In my calculator, if you have y to the x, you have to play around with it a little bit, but I'm pretty sure your calculator is going to want you to do this. 0.5, and then push the button y to the x, and then type 6. And push enter, and that should give you the answer. Now, if you have the caret, it's the same thing. You take 1.05, you then push the button that has the caret, and then push a 6. That caret means raised to. Okay? So 1.05 raised to the 6th power. So either way you've done that, what is our answer here? 1,340. Nope, we didn't multiply by 1,000 yet. 1.34, what? 009564. 0095, okay, so let's say, let's round that to a 01. Okay, 1.3401. Okay, so now we want to go through and multiply that by 1,000. So yes, you could use your calculator, or you could just do what? Move your decimal point 3 spots, because you're multiplying by 1,000. That's pretty easy to do. So we get 1340.1, which since we're talking about money, means 10 cents, right? So after 6 years in an account that pays 5% interest, we would be able to withdraw $1,340.10. So making a profit of $340 for doing nothing, pretty darn good. Questions? Let's take a look at the next example. Now, this next example is not dealing with finances anymore. It's now dealing with endangered species and animal populations. Okay? But they are saying that our table shows the world population for Iberian lynx in 2003 and in 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? So if this was allowed to continue, how many Iberian lynx would we expect there to be last year? Okay? Well, let's find out. First off, we have to decide, are we dealing with exponential growth or decay? Well, they actually said this in the problem, right? Decay. So our equation is going to be what? A of t, little a, 1 minus r, because we're dealing with decay, raised to the t. Very good. Okay. So we can plug in for little a. A of t is what we're solving for, right? All right, so A of, I'm going to leave a parenthesis there because we haven't decided what our time is yet. What is our initial amount? Yeah, they started out with 150 in 2003. 1 minus, we don't know the other information yet. We have to find that. So, first things first, we have to find the rate at which this population is decreasing. Okay, but now wait a minute. Decreasing by 30 individuals, right? Decreasing by 30 individuals. That is not 30%. R is a percentage. We need to find what percent this population is decreasing by. So you're right, 30 individuals, but how do we find R? How do we find that percentage?
120 divided by 150.
Nope, not 120 divided by 150. What are we decreasing by? You guys already said we decreased by how many? 30 individuals. So 30 out of the original 150 is 0.2. So it decreased by 20%. It decreased by 20%. Okay? So it decreased by 20%. So that's going to be our R value, 0.2. But now what about the time period? Our data started at 2003, and we're going up till 2014. How many years is that? Yeah, if you don't know to subtract them, then take your fingers and start counting. Starting in 2003, 1 year from then is going to be 2004, 2005, 2006, 7, 8, 9, 10, 11, 12, 13, 14. 11 years. Okay, so T equals 11. Well, let's plug that in. So A of 11 is going to be 150 times 1 minus 0.2 raised to the 11th power. Doing a little simplification here, we get 150 times what? What is 1 minus 0.2? 0.8 to the 11th power. So, on your calculator, you've got to take 0.8 and raise it to the 11th power. What do we get? 0.085899. We can stop at some point here. Let's stop at 99. Okay. So now we take 150 times that value. What are we getting? 12.88. But can I have 0.88 of a lynx? Well, touche. But we're going to round that down to 12 adult lynx, or at least 12 currently born lynx. Okay? So approximately 12 lynx in 11 years. All right. Astoundingly small population. Okay, we started out with 150 of them, and then 11 years later, there's only 12 of them. Now, in reality, now I'm assuming that this data is correct. I mean, the people who published this book probably wouldn't just make up numbers. They probably had actual information on this. But in reality, do you think that they would have allowed this kind of decline in this population to happen?
No.
No. There probably would have been some conservation interventions going on, conservation of habitat, maybe even some zoos or something might have gotten involved and helped with repopulation, all that kind of good stuff. Okay? So this probably would not have been allowed to happen because at some point in the early 2000s, somebody said, wait a minute, the lynx population is going to disappear. Okay? So, but you can now see how they can estimate those things. All right? How do they know that the lynx population is going to disappear? And is this exactly right? Is this 100% true that if we allowed this to happen, there would only be 12 lynx?
Nature.
Other factors might happen. You know, disease. There could have been a huge flood, and maybe half the population died one year because of a flood. Or maybe all of a sudden something happened and there was a huge boom in their food source, and so then all of a sudden one year the population increased a little bit. I mean, there's lots of other factors involved. Okay, but this is a method of how people then estimate future populations, because actually we have no idea whether or not a certain species is going to reproduce one year or be successful one year or whatever the case may be, but we can estimate it, right? So this is how they estimate those things.